Assalamu alaikum warahmatullahi wabarakatuh. You are welcome to physics class today. We have a topic to discuss known as projectile motion. And before now, we have discussed motion. We define motion as a rate of change in position of a body, and we equally learned that motion of a body is caused by force. We have two classes of forces. We have the contact and non-contact, and then we equally discuss types of motion: rotary motion, linear motion, rotational motion, circular motion, and so on. Now, in this class, we want to talk about projectile motion, and this motion is a two-dimensional motion. It can be discussed in two dimensions. It has the horizontal component and the vertical component. Okay, before we look into it in details, these are the objectives of this class. At the end of this lesson, we are going to be able to identify and explain the properties of projectile, such as acceleration due to gravity, range, maximum height, and trajectory. Then we are going to be able to determine location and velocity of projectile at different points in its trajectory. And finally, we are going to be able to solve problems of projectile motion. Alright, going to discuss your fully. What is projectile? Projectile is the object that undergoes projectile motion. But projectile motion is a curved or parabolic motion of an object in space traveling with constant acceleration. The path through which a projectile motion follows through is known as trajectory. And the force that causes projectile motion is known as gravity. Gravity is the chief force acting on a body undergoing projectile motion. There are other forces acting on the body, but the main one is the gravity. Okay, now we have here pictures of projectile motion. I can see trajectory. The line drawn here is the trajectory. The path through which the ball follows to go parabolic. You can see it here. And in the next slide, we have varieties of pictures showing projectile motion. All these are projectile motion. I can see that trajectory. You can see trajectory, long jump trajectory, dolphin jump trajectory. You can see that trajectory. And this one is a missile that is launched, and you can see the trajectory. Okay, we have examples in sport and in warfare. So let's look at some examples in sport. But before that, all the motion of balls in sports follow projectile motion. Your shot put, discus, table tennis, lawn tennis, football, volleyball, and so on, they all follow projectile motion, like throwing of ball, motion of diver, swimmer diving into swimming pool. You have motion of throwing javelin, discus, shot put, motion of boats in a river, motion of earth moving around the sun. They are all examples of projectile motion in sports. Then in warfare, you have motion of bullet fire from a gun, motion of stone shot from a catapult, motion of a thrown missile bomb, and so on. These are examples of projectile motion both in sports and in warfare. Alright, let's look at terminologies that can be used to describe projectile motion. We have just 4 of them that we are going to itemize here. One, we have time of flight. This one, we have capital T and small t. The small t is the time it takes to reach maximum height, while capital T is time of flight. Then maximum height, we have range, and we have maximum range. Maximum range is obtained when theta is 45 degrees, so you should understand that. Any other range obtained apart from outside, above or below 45 degrees is just termed as range, but the range obtained at 45 degrees is termed as maximum range. Right, so we have pictures here showing projectile motion. We have trajectory. This is the trajectory, And at every point, you can see the two components, the horizontal component and the vertical component. For horizontal component, ux, which is equals to u cos theta, and vertical component uy is equals to u sin theta. At every point, you can see the two components. Then you have to observe that at every point, the ux is constant. The horizontal component is constant at every point. While vertical component varies from one point to another. It varies. It reduces from the point of projection to the maximum height. The vertical component reduces, and when it gets to maximum height, it reduces to 0. So at maximum height, our uy or vy is equals to 0. And when the body is coming down, then the uy is becoming negative, okay, till it lands at point B. Right. Now moving forward, let's now look at these terms one after the other. So what is time of flight? This is the time required for a projectile to return to the same level from which it is projected. It can also be defined as the time taken for the projectile to travel from the point of projection to the point of landing. So we are going to be using the equations of motion under gravity to derive projectile equations. Now for this one, we're going to be using v equals u minus gt. We are using minus when the body is going up, and when the body is coming down, we use g to be plus. We take g to be plus. So this is minus for object going up. It will be plus when the object is coming down. So because the object is going up, we are dealing with the vertical component. So we say vy equals uy minus gt. And in that case, if I try at maximum height, my vy is 0 at maximum height. So if that is substituted there, I have 0 equals to vy minus gt. Let me make t subject of the formula, and that is going to be equals to vy over g. Don't forget that uy over g. Uy is u cos u sin theta, and so my t equals to u sin theta over g. So this is the time it takes to reach maximum height, u sin theta over g. Then for time of flight, the times it takes to reach maximum height and to return to the point of projection. So I have that capital to be equals to 2t. Time it takes to go up equals time it takes to come down. So 2t, t plus t, 2t, and that will give me 2u sin theta over g. So this is the equation for time of flight. This is the equation for time it takes to reach maximum height. We should not mix them together. Right? We can equally refer to that as time it takes to this one. This t can also be called time. This is the time it takes to cover the horizontal distance or horizontal range. Can also be referred to that. Now looking at the maximum height. Maximum height is the highest vertical distance attained as measured from the horizontal projectile plane. So we are going to be using v equals to u minus v square equals u square minus 2gh. That's what we are going to be using here. And at maximum height, v is vy equals 0, and if that is substituted, I have 0 to be equals to u square y minus 2gh. If I try to make h subject of the formula, I have h to be equals to u square y over 2g. From here, I know this one is if this one is transferred to the other side, I'll have u square y to be equal to 2gh. The other side, the other side by 2g, I'll have h to be equal to u square y over 2g. But for vertical components, uy is u sin theta, then all squared over 2g. By the time this bracket is open, then my h equals to u square sin square theta over 2g, and that is the equation for maximum height. Then we have to look at the factors affecting maximum height. There are 3 factors affecting maximum height. We have the initial velocity of projection, we have air resistance, and the final one is angle of projection. All these are factors affecting the height, the maximum height of projectile. And if the higher the initial velocity, the higher the maximum height, and The higher the air resistance, the lower the maximum height. And the higher the angle of projection, the higher the maximum height. Okay. Moving on. We have range. Range is the horizontal distance between point of projection and the point where the object lands on the projection plane. And we have this is the point of projection A, point of landing B. The distance between A and B is referred to as the range. So range, we are using S equals UT plus half GT square. That's the equation of motion under gravity. If that is transformed to what we have here, my S stands for it will be placed with R and UXT plus half GT square or AT square. In this case, my A is going to be 0, and this G will be equal to 0 because the body is not acting under gravity. The body's work is on gravity now, so G has no influence on it and it's going to be taken to be 0. So by the time G equals AX equals 0 is substituted here, I will have R to be equals to UXT plus 0. All of this becomes 0, and that's what I have there. Then don't forget my UX horizontal. I'm using UX because I'm dealing with horizontal component, and that will be U cos theta. Big T is 2U sin theta over G that has been derived earlier, and that is what we have here. Then now have all of these two substituted into this equation. That equals to R equals U cos theta times 2U sin theta over G, and in that case U times U, I will have U square times 2 sin theta cos theta all over G. Now under trig identity, 2 sin theta cos theta is equals to 2 sin theta. We are going to see that when we talk more about identity. So let's just take it in this discussion that 2 sin theta cos theta will give us sin 2 theta. So if I substitute here, I'll have my range to be equals to U square sin theta sin 2 theta over G. Don't forget that this one is replaced with sin 2 theta sin 2 theta. So now I have U square sin 2 theta over G. That is the range equals U square sin 2 theta over G. There's a mistake here. This should be 2 sin theta cos theta equals sin 2 theta, not 2U. This is typographical error. Pardon me for that. Then we have maximum range. Maximum range is obtained when theta is 45 degrees. When angle of projection is 45 degrees. So if that is substituted, you have sin 2 theta to be equals to 2 times 45. That will give you 90. That was a 90, and that will give you 1. So we have maximum range to be equals to U square sin 90 over G, and that will be U square times 1 over G. That will be U square over G. That is maximum range. Alright. And to recap all that we have discussed, we have derived time to reach maximum height to be U sin theta over G. My V naught is U sin theta over G. Then maximum height is U square sin square theta over 2G. Then range is U square sin 2 theta over G. And we have time of flight to be 2 times T. We have time of flight to be 2 times T. And that will be T equals 2U sin theta over G. So these are the equations we have derived. And you don't forget that at maximum height, V is equals to 0. And when the body is undergoing range, the horizontal distance G is 0. At the beginning of projection, T is taken to be equals to 0. Alright. Now let's solve problems with these equations. Number 1, coming from WAEC 2018 question 5, a missile is projected to attain its maximum range. Calculate the maximum height attained if the initial velocity of projection is 200 meters per second and g is taken to be 10 meters per second square. So maximum range is theta equals 45 degrees. Don't forget that. God said body is projected to attain maximum range. Then we have parameters giving u to be 200. We are looking for height. So formula for height is equals to u squared sine squared theta over 2g. By the time we substitute the parameters we are given, we have 200 squared times sine 45 all squared over 2 times 10, and that is going to give me approximately 100 meter. Then number 2, question coming from WAEC 2016 question 2 essay. A projectile is fired with a velocity of 20 meters per second at an angle of 40 degrees to the horizontal. Determine the components of the velocity at maximum height. Component of velocity at maximum height. So at maximum height, don't forget I said at every point there are 2 components. That's why I refer to it as 2-dimensional. This projectile motion is 2-dimensional motion. So at the maximum height, there are 2 components, ux and uy. So your ux is u cos theta. My theta is 40 degrees. My u is 20 degrees. So I'll have ux to be equals to 20 cos 40, and that will give me 15.32 meters per second. But going to the maximum height, uy is 0. Uy is 0 maximum height. That will be uy vy equals 0 meters per second. Right. Number 3 is coming from WAEC 2016 question 9. This is objective. Okay, we have that at a birthday party, the celebrant pops a corked fruit wine. If the cork shoots out of the bottle at an angle of 40 degrees to the horizontal and travels a horizontal distance of 4.5 meters in 1.25 seconds. Calculate the initial speed of the cork. So this value given to you, this one is your range, and this is the time of flight. And range is equals to horizontal component speed times time, ux times time. Ux is u cos theta times t, and we have range to be 4.5 equals u. We don't know the value of u, cos 45 degrees times 1.25. This is time of flight. By the time you make u solve the formula, cos 40 degrees times 1.25, it's going to give you 0.9576 u. Divide both sides by 0.9576. You have u to be equal to 4.5 over 0.9576, and that will give you 4.7 meters per second. Correct option is B. And the last question, we have a tennis ball at an angle of theta attains range equals 78 meters. If the velocity imparted to the ball by the rocket is 30 meters per second, calculate theta. Okay, we are given g to be 10 meters per second squared. So you don't forget that your range is given to be 78, initial velocity to be 30 meters per second. You don't know the value of angle of projection. So we are going to be using range because we are given something about range. So range is going to be equal to u squared sin theta over g. Then we substitute all that we are given. 78 equals 30 squared sin theta over g. If we cross multiply 78 times 10, that will be 780 equals 300. 30 squared, that will give you 900 sin 2 theta. Divide both sides by 900, you have sin theta to be equal to 780 over 900, and that will give you 0.8667. Then you find sine inverse of that value, that is 2 theta equals to sine inverse of 0.8667, and that will give you 60 degrees. Then divide both sides by 2, so theta equals to 60 degrees over 2, and that will be giving you 30 degrees. Alright, this is how far we can go in this discussion. We've been able to